I'm actually doing this from my laptop, so hopefully there won't be any technical issues, knock on wood. Let me go ahead and share my screen, and we will get started today with lesson 12. Can everybody see the paint board?
Yes, sir.
Yes.
Okay. All right. Lesson 12 is a review of various things from Cal 1. The first thing I wanted to go over with y'all today is a review of integration using U substitution. Before I do that, I want to make sure, let's see, Mr. Smith, can you hear and see everything okay?
Yes, sir. It was just loading up. I'm sorry if you would talk.
Oh, no problem. I'm recording this doing this from my laptop, so I just want to make sure everybody can see and hear okay.
Yes, sir.
Okay, the first question in our review of U substitution is a trig problem. And we have the integral going from 0 to pi over 2 of 2 sine of 2 times t all over 4 minus cosine of 2t. Now, at this point in Cal 1, the only other method you learn besides undoing the power rule is U substitution. So that's what we're going to use here. So I'm just going to let U equal to 4 minus cosine 2t. Now, once you label your U, take the derivative of both sides. So the derivative of U is du. The derivative of 4 is 0, of course. And the derivative of negative cosine of 2t, we have to use the chain rule. The derivative of cosine is negative sine of 2t. And the chain rule part of it is we take the derivative of 2t. All right, the derivative of 2t is just 2. And right here, our two negative signs change to a positive sign. So that will give us, once we move the 2 up front, positive 2 sine of 2t. Now, we don't have to divide or multiply by a number, because if you look in your original problem, hang on just a minute. If you look in your original problem, you see that we have 2 sine of 2t dt already in our problem. So that whole thing is our du. And our denominator is our just our u. Now we know the integral of 1 over u, that's natural log. So we have natural log, absolute value of u. Now we need to back substitute what u originally was. Before we do that, did anybody have questions so far? Now let's replace u with 4 minus cosine of 2t. And we need to bring down our limits of integration going from 0 to pi over 2. Now, using our fundamental theorem of calculus, part 2, in place of t, we plug in the pi over 2 first. So we have natural log, absolute value of 4, minus cosine of 2 times pi over 2. In between your substitutions, you guys know we have a minus sign. And the second time around, replace t with 0. Now, going back to the first substitution, the 2's cancel out. And I believe cosine of pi is -1. And we already got that negative sign in front anyway. So 4 plus 1, that gives us positive 5, or natural log of 5, minus cosine of 0 is actually a positive 1. And 4 minus 1, that gives us 3 still. According to my notes, my math lab used a quotient rule for natural logs and wrote this subtraction as a quotient. So our final answer is natural log of 5 over 3. As always, once this video is done processing, I'll share it with you guys later in Blackboard. Any questions before we look at another u substitution problem? Any questions? All right, let's look at another u substitution problem. The integral going from 1 to 3 of 5 times in parentheses natural log of x, and that's raised to the 4th power all over x. Now the first step is to, well, there's nothing we can do except use u substitution. I'm going to let u equal to natural log of x. And we'll take the derivative of both sides now. So the derivative of u is du, and the derivative of natural log of x is 1 over x dx. Now, in the original problem, we can move that 5 in front of our integral sign. Technically, we have now, instead of 5, we got understood to be 1. So we know now that 1 over x dx is our du. And natural log of x was our u. But it's, don't forget, being raised to the 4th power. The integration at this point is very simple. You just undo the power rule for derivatives. So we will add 1 to our original exponent. And that's what we divide our term by, our new exponent. And I almost forgot, bring down that 5. So we're left with 5u to the 5th power, all over 5. We can cancel out the 5s. Now, before we plug in our 1 and 3, we need to back substitute u. So u was originally natural log of x, and it's to the 5th power now. Now, before we plug in our limits of integration, are there any questions, y'all, up to this point? Oops.
So whenever, so where did the u to the 4th come from? Oh, never mind. It's supposed to represent natural law of x to the 4th power, right? Or is it the
Yes.
one over? Okay. So, how did we break it down into du dx again? Like that's what confused me on the homeworks on
Okay.
what to get the derivative of. Cause I see dx, I think to take derivative of everything exactly.
Okay. Were you asking how we got the derivative of natural log of x?
That too. That also.
Okay. This is a property of derivatives that just go back and review. It's just a derivative rule, a general derivative rule for natural log.
Oh no. I was asking how did we determine that was going to be u? Like I don't know.
Oh, good.
I don't know how to explain it. Like how you have.
I think he's confused on what you substitute with u.
Yeah, like how did you determine like this is going to be u, and I understand derivative of u. You just took the derivative of the ln, which made it automatically 1 over x. I was just asking for future references and problems. How do you determine when something's going to be u?
Okay, gotcha. To be honest, it's trial and error. Like if I let u equal x
Mm-hmm.
and took the derivative,
It'd be 0 or 1 or whatever.
yeah, that would actually lead us nowhere because, yeah, we got the dx here to plug in, but we
Yes,
got
sir.
all this stuff up here
Yes, sir.
that's still left over. So it is trial and error. If what you pick doesn't work the first time, then try something else.
Okay, so like with the problem previously, we could have chose 2 sine or 4 minus cosine.
If you had chosen the 2 sine of 2t,
Yes, sir.
you would see right away that there was nothing that would match when you take the
Uh,
derivative.
yes, sir.
Yeah, it would actually be 4 cosine of 2t, and when you take that derivative,
Yes, sir.
and yeah, that's nowhere in the problem.
Uh,
So if you see what you pick for you will make the problem more difficult, then pick something else and see if that works.
yes, sir.
Did that help? Did that answer your question better?
Yes, sir. A little bit.
Okay. Yeah, I wish I could tell you there's a magic formula, but with U substitution, there's really not. It is truly just trial and error. And also, the view and examples do help. I mentioned that before in a previous video. Kind of help you master how to pick the right U for substituting. But you'll definitely see right away if you pick the wrong U, then your problem is going to get more difficult. All right, plugging in our limits of integration. We have down here natural log of 3 to the 5th power minus natural log of 1 to the 5th power. The natural log of 1 is 0, so that second part goes away entirely. And our final answer is just natural log of 3, all raised to the 5th power. Now, if you guys took it a step further and moved the exponent in front and made it 5 natural log of 3, I would mark that correct also. Are there any other questions before we look at another U substitution problem?
I just need a minute to copy this now.
Oh, okay.
It's going to take a few seconds.
Oh, that's fine. We're going to look at another integral where you have to do U substitution, and it also involves a trig function. So we'll take another look at one of those in just a minute. Make sure that you have in your notebook somewhere, go to Google and print out or just search list of integral tables PDF and go ahead and print those out from one of the websites and stick that in your notebook because it will become very handy later on when we talk about other ways to integrate. And there are some integrals, some problems that just simply cannot be integrated by conventional means, and you have to use a particular formula to plug in the values and get the integral, because trying to integrate it by hand using other ways is impossible. Okay, let's look at another question involving a trig function and also U substitution. We have the integral going from 0 to 7 pi over 4. of, now I'm going to go ahead and move this constant in front, 6 on the outside, and then tangent, this is a fraction, x over 7 dx. Now, we're going to use substitution here to figure this out. And if we let u equal tangent, then the derivative would be secant squared, and we don't have a secant squared to plug in. So let's make it easier on us and let u equal to 1x over 7. Now, when we take the derivative of both sides, the derivative of u is du. And the derivative of 1 over 7x is just 1 over 7 dx. Now, the only thing that we need to plug in to our original problem is the dx part, and of course the u part. But over here, we don't have dx by itself. We need to multiply to get dx by itself, both sides by 7. So dx is equal to 7 du. Now we're ready to plug in our u and also our dx. Now that 7 goes outside with the 6. And when we multiply those together, we get 42. Tangent. And in place of x over 7, plug in u. And we're ready to integrate. Any questions about the substituting part?
So whenever it's a fraction, we just multiply it to get dx by itself. Or is
Right,
that
it's usually, yes, sir. It's usually you're either multiplying by the reciprocal of whatever number is here that you're trying to get rid of.
yes, sir.
If it had been, say, for instance, 3dx, then you would just divide by 3 to get dx by itself.
Yes, sir. Okay.
Now, the integral of tangent u is one of our basic trig integrals. And it is actually a natural log, absolute value of secant u. Now, before we plug everything in, our limits of integration, we need to back substitute what u originally is. So in place of u, plug back in x over 7. Oh, I'm sorry. Bring over the 42. And now we're ready to integrate this from 0 to 7 pi over 4. Now, first up, when we plug in 7 pi over 4 for x, We have 42 natural log of secant of 1/7 times 7 pi over 4 minus natural log absolute value of secant of 1/7 times 0. So I just used the fundamental theorem of calculus and plugged in our limits of integration. Now, right here, the 7's cancel.
Is that
And
is that 1/7 times? Oh, 7 pi. Oh, okay, I didn't see that.
no, I'm sorry, I didn't write it clear enough for everybody.
Yeah, you're fine. I just couldn't tell what it was.
Now we're trying to find secant of pi over 4. And whether you use your calculator or look online, secant of pi over 4 is exactly square root of 2. All right, the second part, we're trying to find secant of 0. And secant of 0 is equal to positive 1. Now, natural log of 1 is 0. And we're left with 42 times natural log of square root of 2. Now, for me, you can leave your answer like this, but my math lab went a step further. Let me show you what my math lab did. They rewrote square root of 2 as 2 to the 1/2 power. And then my math lab used the exponent rule for natural logs and moved the 1/2 to the front and multiplied it by the 42. Two can go into 42 21 times. So this is the answer that my math lab got, but I would accept either answer. Are there any additional questions about this problem? Okay, another thing that you'll see in lesson 12 is kind of a review. Is what's called a differentiable equation. Can you guys see that okay on your end?
Yeah.
Okay,
Yeah,
thank
we can see
you.
it.
This example is called a differential equation, where you're still using integration and you're solving for a particular letter or a combination of letters. Now, if you have a combination of letters, if it was a derivative we had to find, then we could use implicit differentiation. But for integrals, we have to do something a little different. So let me read to you this information. It'll help us solve this equation. A differential equation dy over dx equal to f of x and y. In other words, your function is in terms of two letters, not one. A differential equation in this form is separable if f can be expressed as a product of a function of x and a function of y. Let's put this in more common terms that we can work with here. In other words, when you have a differential equation like this and you're trying to solve it, you want to get all of your x's, including the dx, on one side, and you want to get all of your terms that contain a y on the other side. So that's what we're doing here to solve this particular equation. So let me copy and paste this to our paint. All right, before we can solve this differential equation, we need to get everything with an x on one side and get everything with a y on the other side. Probably the best thing to do is multiply both sides of your equation by dx. If that gets us nowhere, no problem. We can start over. The dx's cancel out, and you're left with dy equal to 5x to the 7th power times square root of y, or y to the 1/2 power, times dx. Well, we got all the x's together by on their side, but there's a y term that we need to move. So to get the y term on the other side with a dy, just divide both sides by y to the 1/2 power. Excuse me. That's what you're trying to do with the separable differential equation. You're trying to get all the same letters on the left side and all the same letters or x's on the other side. Now we can rewrite that y to the 1/2 power as y to the negative 1/2 power, just to make it easier to integrate. Now, before we go on to the next step, did y'all have any questions up to this point? Now, once you get your letters separated, that's why it's called a separable equation. You integrate both sides. Now, on the left side, actually both sides, we can use the power rule in reverse. So on the left side, we'll add 1 to the original exponent. And we divide by our new exponent, the negative 1/2 plus 1. So this simplifies now to y to the 1/2 power all over 1/2. And because we're dividing by a fraction, that fraction 1/2 in the bottom is going to flip. So this will become 2y to the 1/2 power. Or just 2 times square root of y. Because we're not plugging anything in, specifically no limits of integration, we have to put plus c, or in this case, c sub 1, to represent any possible constant. Now let's do the same thing to the right side with the x. Again, we'll add 1 to the original exponent. And that's what we divide by the new exponent. So that gives us x to the 8th power all over 8. That 5 is already there, so 5 times 1/8, that makes it 5x to the 8th power all over 8, plus c sub 2. I'm using different subscripts because we can't really say that those two constants will be the same. Now, the last step is to get all of the different constants on the right-hand side. So if I subtract c sub 1 from both sides, well, a constant minus a constant is still a constant. So we'll just label that as plus c at the end. And that's how MyMathLab wants the final answer. You don't have to solve for y, you can leave it like this. Any questions about solving a differential equation? All right, this next example also involves a separable differential equation. It's a word problem. So let me screenshot it, put it on our whiteboard here. Let's see, here we go. Hang on just a second, y'all. Can everybody see the word problem okay?
Yes, sir. Yes, sir.
Thank y'all. Okay, let me read the word problem to you and we'll figure out what we need to do. For a particular chemical reaction, the rate in grams per hour at which one of the reactants, changes is proportional to the amount of that reactant present. If Y represents the amount of that reactant at time t, then dy over dt is equal to negative 0.1 times y. So in other words, the change in the amount of the reactant at time t. That's what the dy dt represents. If there were 50 grams of the reactant when the process started at t equals 0, how many grams will remain after 2 hours? First step is bring down our differential equation. And we have to separate the letters. So what I'm going to do is multiply both sides by dt. And again, if that leads to nowhere, we can start over. That's not an issue. So we have dy equal to negative 0.1y times dt. Now we can leave the negative 0.1 where it is, but we need to move that y to the left side with the dy. So let's divide both sides by y. So that gives us 1 dy over y equal to negative 0.1 dt. Once you've separated the variables and got them on their individual sides, the next step is integrate each side. On the left side, the integral of 1 over y dy is a natural log of y. And on the other side, the integral of 0.1 dt, that's like taking the integral of negative 0.1 dx. It's just going to be your letter with the constant. Oh, and I forgot the plus c, excuse me. Now this next step, don't forget, because I almost did, we're trying to solve for y, trying to get some type of equation here. To get y by itself, you'll need to take base e to both sides. There is a property you guys know from algebra and or pre-cal where if you have e raised to the natural log of anything, then your answer is just anything. So on the left side, e to the natural log of y is just y. Now, let me show you how to simplify the right-hand side. Because we have addition, you guys know from exponent rules and natural log rules that if you have addition, then that started out as a product, kind of going backwards here. So we can rewrite the right side as e to the negative 0.1 t times e to the c power. Is everybody okay so far? Just want to make sure. Now that e to the c power, that's saying that you're taking e and raising it to any constant. So if you're taking e and raising it to any constant, then you're still going to get a constant. Just for clarity's sake, this e to the c power, let's rename that as c to the c sub 1 power. So we have our equation now, y equal to c sub 1 times e to the negative 0.1 t. Now we're actually going to use this equation. The c sub 1, let me go back up here for a minute. The 50 grams, the c sub 1 stands for the initial amount. So the initial amount is 50 grams. And what we're trying to find is how much is left after 2 hours. All right, so in place of t, just plug in 2. Now, when you plug all of this into your calculator, you will get roughly 40.9 grams.
Mr. Arnold.
Yeah.
Back up a couple steps where you had e to the negative 0.1 t times e to the c power. Could you plug that 50 into that part?
Good question. You would actually have an extra letter, because at that point you don't know what C is just yet.
Okay.
Like right here, yeah, you could plug in 2. And I suppose you could plug in 50 right there.
Yeah, that's what I was thinking. Could you just plug in the numbers at that point?
You know what? Let's do it. Let me share my calculator. Hold on. Okay. E to the 50th power. And I'm sorry, I know that's really small. Oh, there we go. Times 0.1 times
Well, it's negative
2.
0.1. Okay.
Yeah. E hold on, something tells me I did something really wrong. Let's see. e to the 50th power times, in parentheses, 0.1 negative times 2 to e No, that's still not coming out right. Okay, 50th times 0.1 negative. You know what? Let's see. We already know what it is. 0.2 negative to the e. Yeah, to answer your question, you would have to wait because it'll give you a completely different answer.
All right.
Yeah, I'm glad you asked. Even after 2 hours, it shouldn't have decomposed that fast. So yeah, I'm glad you asked, and the answer is wait until the very end. Change this part to another thing, to C sub 1. And then you'll plug in everything and you'll be just fine. Are there any other questions about this problem? Okay, I didn't go over every single question from this lesson. There are some other word problems that you'll encounter. For the homework, of course, you have view an example and you have me at your disposal. If y'all need help me explaining something, just let me know. What I can do is, if you have a question about something, I can at home use my laptop and make a quick video demo helping you out with this example, or the example that you had a question about. Are there any questions about lesson 12? Oh, excuse me. Looking ahead to next time, we will go over lesson 13, and that deals with, I can never pronounce this correctly, hyperbolic functions. So we will go over the different properties and look at plenty of examples for next time.
Mr. Arnold, I have a general question.
Yeah.
On Blackboard, it says that this batch of assignments is due this week. Is that still correct? Or is that an error?
Oh, no, I will change that. Thank you for reminding me.
Okay, no problem.
Hey, Mr. Arnold.
Yes.
Well, how do I explain this? Are you still taking off a few questions